Good afternoon. It's been a fascinating conference so far. There's one thing that sticks out for me, and that's that as human beings, we are remarkably creative. You only have to look at the work that the Disney Imagineering folk are doing, and Boston Dynamics, and that's one of my favorites. You sort of wonder when the robots will get a bit creepy, though, getting into that stage. So it's been an impressive, very impressive start. One of the other things today, Zoox, the autonomous vehicles. I've got a 5-year-old daughter, 8-year-old daughter, and very hopeful that that'll be done before they hit the road. So I don't want them to be driving. And traditionally, we're not the best drivers. So we're going to talk today around how Kinect Energy is using Amazon SageMaker and machine learning to help predict natural power prices. The genesis of this idea came up, like many ideas, over lunch at a place called Sushi Joe's in Miami, the type of place that hasn't put up its sushi prices for the last 20 years, very cheap and cheerful sushi place. So we'll talk a bit about how we came to the idea, a little bit about the energy market dynamics that are really interesting lately, and also what we're doing with SageMaker. So when we talk about the energy market, really we're entering this period of unprecedented energy market volatility. When we talk about volatility, what I mean is price, so the fluctuation on energy prices. In the US, it hasn't been this volatile since the 1950s, and according to Carnegie Mellon research, we've had 9 major price fluctuations over the last decade, and that's compared to just 7 for the preceding 3 decades before that. So it's getting more volatile. I think we all remember the collapse in oil prices when oil went down from $100 a barrel to $30 a barrel and the global implications of that. And we're seeing a lot more renewable energy hit the market, and that's a good thing. But the more renewable energy that hits the market, the more supply and demand imbalances start to come through, which drives up volatility. So we'll talk just briefly about what's driving that volatility. This is not an exhaustive list by any means, but these are some of the more interesting factors. And the first is around fracking and natural gas. And just to explain what that is, fracking is a relatively new technology, and it gives us the ability to extract oil and natural gas from deposits that you previously couldn't get to, or they were just not viable to get to in the past. The outcome of that is, for the first time in 60 years, the US is now a net exporter of natural gas, and very soon to be a net exporter of oil as well. So if you just think about that for a second. Leading into the next point around geopolitical tension, we know that areas like the Caucasus, we know areas like the Middle East are used to having quite a large supply overhang of oil. What tends to happen when you have a supply overhang, you add that in with the production coming out of the US, you don't have a cushion anymore to absorb any price shocks or geopolitical tension in those regional areas, and that tends to spike volatility as well. From a macroeconomic point of view, I've talked to a lot of folk here who are engineers, a lot of folk at the conference who are running energy companies, and the one memory that we all have is the GFC was a tough time, global financial crisis. So the ability during the GFC to continue energy projects was under threat. So a lot of energy production was cancelled and had knock-on impacts. So we're seeing, again, the ability to assess the long-term viability of energy projects is tough. And the ability to get credit consistently for those projects is tough. So it moves on to the weather as well. I think weather is, regardless of your views on what's causing it, we are seeing more frequent and more severe weather events around the globe. That also impacts volatility because, as you can imagine, both on the supply side and the demand side, when you have a severe weather event, sometimes that impacts your production of energy, sometimes that impacts the demand on energy as well. So more and more we're seeing this volatility around price. So why is that a problem? If you're a large commercial or industrial company, energy is one of your biggest costs. So you have to have a view of your global energy spend, and you have to be smart about how you procure that. That's what we do at Kinect Energy. We help our customers buy better and buy less energy. So we come up with these strategies for large commercial and industrial companies on how you procure your energy, what sort of mix of renewables you need, how you comply with local legislation, and so on. So that's what we do. That's the customer proposition. A part of the broader World Fuel Services group. World Fuel is a Fortune 100 company headquartered in Miami, right next to Sushi Joe's. And one of the things we invest in is really a strong culture of innovation. And the reason we do that is the services we provide our customers rely on the people that we have. So what's really important to us is that we attract, develop, and retain great people, and we work very hard on the type of culture and innovation that we support. Because there is a lot of volatility in the market, and we do see the services really changing and evolving as we go through. So I'll give you just an example of some of the things that we do. We're helping Gatwick Airport with their goal of being 25% renewable by 2020. We also helped a large European industrial company save 4.2 million euros off their annual energy bill. This is a different customer example, and what you're looking at there is a 2-year price for energy. So if you look at the red line, what you see is effectively energy prices are more than doubling over a 2-year period. So you can imagine if energy is one of your largest costs, that can sometimes mean the difference between making a profit and not making a profit. So what we do on the blue lines there is keep that energy price consistent within 10% of the starting point, which is a very valuable service that we have for our customers. And we've done that, and we've been very successful with that. But with machine learning and all this additional data that we can look at, we think we can do a better job of that. So we think we can make that even better again. Just to give you a sense on how the power market works and some of the dynamics that we have to consider. This is a European example, and I think, as I've said before, each of these energy markets are subtly different. So you're thinking about different factors every time you're trying to model what's happening with power and power prices. Every region, for example, will have different regulation. They'll have different preferences when it comes to renewable energy. They'll have different subsidies, and people will have a very, very different approach on how they want to consume energy. So our job is to look at all those factors and consider them. So in the European example, when we look at volume, when there's a lot of wind, when there's a lot of rain, we have cheap wind and hydro. That kind of makes sense. When there's not, we have to rely on more expensive sources of power like coal and natural gas. When it's colder in the European context, people want to stay warm. So they use more heating, spikes energy, and then spikes demand, and again, we have to consider that. Opposite to what happens outside here in Las Vegas, obviously, when it gets hot, people need to cool their homes, and again, they consume energy in that way. So these are just some of the factors that we have to consider. When we look at these factors within the models that we do today, we've done that very, very well on a longer-term basis, but the opportunity is around using cloud, using machine learning and Amazon SageMaker to do this in a highly automated fashion and do that in real time. And that's what we've started doing. Just to go a little deeper on how the markets work in terms of energy, what we focus in on is the current system price. And the current system price is a calculation of all of the demand that's projected over the next 24 hours. So what happens, that demand gets loaded into the market, and the market determines a price on that. So if you're a producer of energy, let's say power station or wind farm or anyone that produces energy, you decide then whether you want to produce that energy for that market in the following day. It's likewise consistent across a 4-week period, same calculation and same focus on that current forward price. So if we can do a better job of predicting that, if we can ingest more data and run the algorithms and do a better job of predicting that, then what we can do is help smooth out our customers' energy consumption and smooth out the energy price on their behalf. So that's the value that we provide customers. The better job we can do of predicting the power price, the more efficient energy consumption they can have. So what that means is, we really focus in on this 1 month time frame, and that's been very successful for us. So the projections are in 2019 we can do 6 times the amount of trading on that 1 month time frame, and that's all value that we can pass on to our customers. Internally, we're a cloud-focused and cloud-first company already. We're getting out of the business of running our own data centers. Number one, because we're not very good at it. Number 2, it's expensive, and number 3, when it comes to data centers, we'll never outbuild or out-innovate Amazon. So we've partnered with Amazon to run our data centers, and the use of SageMaker is really a very natural linkage to that. So one of the pieces around why we chose SageMaker, traditionally if you wanted to get into the machine learning space, you needed an army of very technical data scientists. I think Werner Vogel's talked about it this morning, that with machine learning, it essentially, and SageMaker, it democratizes machine learning. So regardless of what your business is, you can now get involved very quickly with machine learning with just a couple of very smart people and use these platforms to create the models and get the outcomes like this. So we're looking to optimize this even further. I think machine learning should be sprinkled in across all areas of our business, and we see a lot of potential with this going forward. So what I'll do now, I'll hand over to Elena, and we'll go into a deeper dive on the product itself. Thanks.
So I'm Elena. I'm one of the data scientists at Amazon Web Services. I want to begin by going over our AI and ML capabilities, and then I want to dive deep into how we leverage these for Kinect Energy's use case. AWS has the broadest and deepest ML capabilities for our customers. Specifically, Amazon SageMaker takes machine learning and it puts it into the hands of your data scientists and your developers. In the last year, we have released over 200 new services and features. No other cloud provider has produced half as many, and our pace is only increasing. Specifically, I want to focus on this middle tier. This middle tier contains Amazon SageMaker. SageMaker is our fully managed machine learning platform. It takes all the required steps you need to build, train, tune, and deploy your model into production. Before SageMaker, machine learning was just too difficult, and like Richard said, you need to have a team of experts. But now it makes it much easier for your team to build ML models at scale, quickly, and at lower cost. For example, Intuit is one of our customers. They build machine learning models that take years' worth of bank transaction data and identify business deductible expenses. Previously, this development for machine learning models took them 6 months, but with SageMaker, it took them 1 week. This is a reduction in time of 90% development. In the last 2 years, since SageMaker was released, over 10,000 customers have adopted SageMaker as their machine learning platform. I want to walk you through the ML pipeline using SageMaker. First, you might begin with ground truth. Ground truth is a tool that lets you build a very highly accurate data set, and it can also reduce your data labeling costs by up to 70%. From here, with 1 click, you can provision a SageMaker instance notebook. This uses the popular interactive Jupyter interface. Within the SageMaker instance, you have access to the top ML algorithms that are used. At Amazon, we have specific teams that have optimized the performance of these algorithms so that when you run them within the SageMaker environment, they achieve 10x the speed that they would in any other environment. Training is also very easy in SageMaker. To train one of the built-in algorithms or your own custom algorithm is very simple. With 1 click, you can spin off a training job that can scale to deliver a petabyte model, a model of petabyte scale. You will also want to tune your model or the hyperparameters of your model. For this, SageMaker has a feature known as automated model tuning. Once your model is trained and tuned, you'll want to put it into production. With one click, you can deploy your model as an endpoint. This endpoint will behave like an API in your production pipeline. We want to make it easy for our customers to put machine learning into practice. We have a program known as the Amazon Machine Learning Solutions Lab that I'm a part of. The Amazon Machine Learning Solutions Lab is how WorldFuel Services first connected with AWS. The way the program works is that first, our machine learning business developers, they go and they meet with you, the customer. They help you formulate your machine learning use cases, they help you prioritize them, and they help you scope out the resources. This includes time, costs, job role type, et cetera. Then, our data scientists come in and they work with your data science team or your developers. We help you build the ML model for your use case, but we also help you build the ML pipeline to put this model into production. It's very important to us that the ML pipeline that we deliver integrates easily with your workflow and is influential for your stakeholders. The overarching theme here is that we want to teach the customer to fish. We don't want you to become dependent on us, on our data scientists. We want you to have the tools to go out, maintain the solution, iterate upon the solution, and improve upon the solution ultimately. I want to go into detail on the solution that we built, the Machine Learning Solutions Lab, with Kinect Energy's team. Kinect Energy wanted to forecast energy prices 4 weeks in advance, and they wanted to have hourly increments of these forecasts. In order to begin building this model, we looked at 3 types of input data. One, we looked at electricity time series over a 4-year period. This is data from 2014 to 2018. Secondly, we looked at energy consumption data and energy production data from different sources of electricity generation. And lastly, we looked at any data that has a direct influence on this. This means weather data and hydrological data. We have 2 main goals here. One is we want to create the actual ML model that can deliver very accurate forecasts 4 weeks in advance. But the second one is equally as important, and this is to package the ML model up as an automated forecasting tool. And we need to make sure that this automated forecasting tool performs reliably in Kinect Energy's production pipeline. I want to walk you through how we built this model and the architecture behind it. Okay, we start in stage A for data acquisition. We create Lambda function number 1. What this does is it goes and it collects the input data that we desired by pulling the data from a series of external APIs. It takes this data and in this raw JSON format, writes this to our storage S3 Amazon bucket. We create Lambda function number 2, and in this function, we perform most of our data preprocessing. What this includes is type conversion, error checking. We also perform some data quality checks. For example, any time series that had a high proportion of missing data, we don't want to include. And any time series that had its data being reported on an irregular basis, we want to exclude. The rest of it we write in CSV format, and we write back to the S3 bucket. Now we have a structured data set that has consolidated all of our historical time series data. With this, we can now proceed and perform our exploratory data analysis and our feature engineering. One thing you'll notice here is that everything is contained inside this white dashed boundary. This means that all of your modeling and all of your model evaluation is being performed in a single SageMaker environment. I want to walk you through this process of the architecture the same way we walk through a modeling problem. So we have hundreds of time series, some of which are very correlated. And this is very problematic for modeling. Principal component analysis, PCA, is an algorithm that lets us create a decorrelated data set. It also allows us to reduce the dimensionality of our problem. One thing we found is that instead of using hundreds of very correlated features, we went to using fewer than 10 decorrelated components. and this greatly improved the accuracy of our subsequent modeling steps. PCA is one of the built-in algorithms that comes with SageMaker. What we don't do is we do not pass our data directly into PCA in memory. Our data is already residing in the S3 bucket. What we do instead is we take the S3 path location and we pass this into SageMaker. Once you click the training job and the training job spins up, SageMaker knows where to look in S3, and it knows how to read this data in an optimized and parallelized fashion. The training job completes, and SageMaker writes the model artifact back out to S3 at a location that you specified. What's nice about this is we can either take the model artifact and we can either use it to spin up an endpoint, or we can port it into another environment. Next, we take our PCA transform data and we have to reformat it. We have to convert it into a format that is digestible for our deep autoregression model. DeepAR is also a SageMaker built-in algorithm. I'm going to go into detail on this algorithm in a bit, but for now, it performs the same way in the sense that you pass in the S3 location, not the data in memory directly to it. It trains the model, and it writes its model artifact back out to S3. For DeepAR, it is very important that you tune its hyperparameters to increase its model's accuracy. To do this, we use SageMaker's automatic model tuning feature. This performs a managed Bayesian search over our hyperparameter space. It takes the best trained model, like best accurate model, and writes this one back out to S3. And now we can consider this our final model. But what is DeepAR? DeepAR is a supervised algorithm. It uses autoregressive recurrent neural nets and Monte Carlo simulation to produce probabilistic forecasts. The original algorithm was developed by Amazon for its retail product demand forecasting. But now we've included it inside SageMaker so that our customers can use it to solve their time series forecasting problems. DeepAR was a good fit for us, both for our data and for our goal. We wanted to predict many different energy prices for different regions. And we could have been stuck having to tailor multiple models for these. But instead, with DeepAR, we can yield a single model that provides us with multivariate forecasts. We also wanted to experiment by including different types of covariates and categorical covariates to see what is influencing and what might be beneficial to our model. This could have added a lot of complexity. DeepAR makes it easy for us to specify our dynamic and our categorical variables and let us know which ones are important. Kinect Energy told us that it's very important as well that we quantify the variance around the forecast estimates. This is not a problem since DeepAR provides us with confidence intervals. Most importantly, like I said, we had lots of time series data, and we don't want to have to extract seasonality patterns for each one at the weekly, daily, and yearly levels. What's nice about DeepAR is it handles a lot of this feature generation for us. Most forecasting algorithm implementations assume that your data is already complete. But in reality, this is rarely, if ever, true. Especially with time series, it's very often that you'll have missing observations, missing values. DeepAR handles this by using its recurrent neural network model, instead of using a coarse grain imputation technique. This is how it's able to produce more accurate forecasts. It can also be very useful or very beneficial to include explanatory context around certain periods of your data. Let me give you an example. You might have known that there was a promotion on for a certain period of time. And being able to specify this might help your model realize that this explains the sudden but temporary surge in demand you saw later on downstream. DeepAR lets you specify these custom features. And conversely, you can use DeepAR to simulate what-if scenarios, such as what if I put a promotion on for the month of July? How will this impact my sales volume forecast? Categorical information can also prove to be quite insightful. You might have a product that at a high level belongs in the category of clothing as opposed to electronics. Or within that category, at a lower level, it belongs with shoes as opposed to t-shirts, flip-flops as opposed to sneakers. Or you might break it down according to brand. Being able to specify this categorical information in DeepAR means that DeepAR can learn multi-level granularities. It can learn its seasonality patterns, and it can leverage that behavioral knowledge to produce more accurate forecasts. real-world big data problems also tend to exhibit the power law relationship. What I mean by this is an example of, let's say you have some products that sell exponentially high, and conversely, or relatively, you have many products which have very low sales volume. What this is going to mean is that you will have a few time series with very long histories and many time series with very short histories. And this is going to create two problems. This creates exponentially autoregressive nonlinearities. It also creates inbound sample sizes of your data series. In the DeepAR algorithm, they've created an item-dependent scaling, which overcomes both of these issues. Usually with forecasting models, the most laborious part and the most time-consuming for sure is all of this feature engineering. As we've just seen, DeepAR handles a lot of this feature engineering for us. What you need to focus on now, or what as a lesson learned that we did, is you need to focus on making sure that you correctly input your metadata so that it represents your data accurately. I'll just walk through this example. We see the start time. It's a date time in the format of a string, and you only see one. This is because you have to have the same start time for your target variable as for your dynamic covariates. Another thing you'll notice is that DeepAR is supporting missing data in its target variable, but DeepAR is not supporting missing data in the dynamic features. And of course, you also have to specify your categorical information correctly. Dynamic features, or dynamic covariates, they are not your target data, but they are any other data that might influence or be correlated to your target variable, and you want to leverage this for your prediction accuracy. One thing that I want to make sure is clear, and this is not specific to DeepAR, this is for any kind of time series forecasting, is that any dynamic covariates that you used in the past to train your model, these need to be available in the future to make your predictions. So for example, if in the past you used weather data and you trained your model on this, you need to have future weather data available in order to make your price predictions. Now, we know this is not going to happen because we have yet to observe future weather data, right? OK, so instead, you can put in weather forecasts. But what's important is that you need to make sure that the forecast error for your substituted variate is less than the variance of your target variable. Otherwise, you're introducing uncertainty into the model. I also want to discuss context length. Context length is how many data points back your model looks when it's making a prediction. In general, for other models, you might need to have a very extensive context length to be able to capture the full history. DeepAR handles a lot of the feature lie generation for us, so you don't really need to have this extensive context length. We recommend you have a context length equal to prediction length, where prediction length is how many data points in the future we want to look. You might remember that for Kinect Energy, they want to look 4 weeks in the future at hourly increments. In general, we recommend that you don't have a prediction length that exceeds 400 if you want to have DeepAR's best performance. For DeepAR, these are the key hyperparameters that you want to have tuned. The dropout rate, the embedding dimension, the number of cells per layer, and how many layers are in your neural network. These control the greediness of the algorithm, the complexity of the algorithm, and the embedding dimensionality for your categorical variables. For us, we used SageMaker's automatic model tuning. This, like I said, this performs a fully managed Bayesian search for us. But what's important here is that you want to specify the maximum number of jobs. Otherwise, this could blow up very quickly. For us in our problem, each training job took about 1 to 2 hours. We specified a maximum of 30 training jobs. We were operating on 2 parallel instances of size C4 16 extra large. This meant that our hyperparameter optimization job took a few days to complete. When SageMaker's automatic model tuning finishes its training job, it takes the best performing model and writes it back out to S3, and we can consider this our final model to deliver Kinect Energy their 4-week forecasts. Like I said at the beginning, this is the end of goal 1. We now have our final ML model, but we still need to accomplish goal number 2. We need to package our ML model into a reliable pipeline to deliver these forecasts to Kinect Energy stakeholders, i.e. their portfolio management team. You see here that we repurpose lambda function number 1. In the training, lambda function number 1 was pulling full historical archival data in order to build our model. For making daily predictions, we don't need this. We repurpose Lambda function number 1 so that it only pulls the daily incremental data, and it writes it in the JSON format to S3. Next, we repurpose Lambda function number 2. It performs the same type of data preprocessing on the daily incremental data and pushes it back to S3. Now, we have consolidated our historical data from before with today's daily processed incremental data. We create Lambda function number 3. This Lambda function performs a call to the SageMaker batch transform. This batch transform is quite clever. What this batch transform allowed us to do is it allowed us to package together our data preprocessing, our PCA transform, and our DeepAR predictor into a single endpoint. What this means is relatively raw data is coming in, it hits a single endpoint, and outputs the energy prediction prices. What's nice about this batch transform is that it is a one-time call that performs batch predictions. So you do not need to persist a live endpoint. The energy prices that were outputted, we push into the Amazon Quick site to generate a dashboard. And we have this set as an automated email to the Kinect Energy stakeholders. I want to dive a little bit deeper into AWS Lambda, AWS step functions, and down the road, I'm going to talk about inference pipelines. These 3 things really helped us make sure that the model we built can perform in a reliable environment, and it protected us against potential situations of failure. AWS Lambda allows us to run, or allows you to run, code for virtually any type of application or back-end service. You simply upload your code into Lambda, and Lambda is responsible for taking care of all the requirements that will make sure that your code runs and scales with high availability. AWS step functions allow us to coordinate a series of AWS services into a serverless workflow. What this means is the output from one step will be the input for your next step. We set up our AWS step functions to be triggered by a particular CloudWatch event. We know this CloudWatch event happens every day, and we want to have a daily cadence of predictions. You'll remember that our second Lambda function number 2, is the one that performs our data preprocessing. This data preprocessing depends on certain Python libraries, like scikit and like pandas. These libraries do not come native with Lambda. In order to install any package dependencies, you download them to your Linux environment, you install them, zip them up, and you upload them back into Lambda. We also used our step functions to construct fail-safe mechanisms for any potential points of failure that we identified along our pipeline. Let's take the example where the website is down. This means that it's going to return an error when we do the API call for Lambda function number 1. We took advantage of a functionality that step functions has called retries. For this, we can specify for a particular error how many retries we want to make, the interval between the first between the first attempt and the first retry, and whether to keep this interval or whether to double it for each successive retry. In the case where the website is down, the step function knows to try 5 more times at increasing intervals. If we still get an error on the 5th try, the step function will switch Lambda number 1 from its daily incremental pull to pulling a full historical archive. And thus, we recover our pipeline. A second point of failure that we identified is that, OK, the website is not down. It works, but the data on it has not been refreshed. This means that the API will actually not give us an error, but we're introducing data corruption into it. For this, we've specified in the step functions, try 8 times, but at equal interval. And if it still fails, then again, switch Lambda function number 1 from its daily mode into the mode where it does a full archival pull. You might remember Lambda function number 3. This is the one that performed the SageMaker batch transform call. Lambda has a size limit of 50 megabytes. But this call would have relied on the SageMaker SDK library. And this library, even when it's zipped, exceeds this limit. To circumvent this, we used a lighter SageMaker library, Bodo 3. With Bodo 3, it fits within the Lambda size limit, and we're able to still create a request for our endpoint invocation. we found it very beneficial to use Amazon SageMaker's pre-built containers. One of the containers in SageMaker is a Docker container that comes with scikit-learn libraries configured. This means that we were able to use scikit-learn estimators, but with SageMaker functionality. So scikit-learn estimators, but with one-click training, one-click deployment, and hyperparameter optimization. Another thing that is very useful here is this entry point. What this entry point allows us to do is we can supply it with a custom script. And in this custom script, we can specify the model functionality that we want, what kind of data pre-processing operations we want, how we want to perform our train test split, hyperparameters, and any post-processing, et cetera. This is how we package together our pre-processing, our PCA transform, and that post-processing that was necessary in order to format our data for the DeepAR ingestion. SageMaker inference pipelines allowed us to set up a series of Docker containers. And in this pipeline, the invocations of this pipeline, they kind of perform like HTTP requests, where the response from one container will act like the request input for the next container, and so on until the final response is returned back to the client. This is how we set up a sequence of 2 to 5 containers. And these 2 to 5 containers, this is how we combined our custom pre- and post-processing algorithms with SageMaker's pre-built algorithms. This means that a single invocation triggers the entire pipeline. This also gave us inference consistency. And what I mean by inference consistency is that same pre-processing steps that we learned during the modeling pipeline, we want to make sure that these are carried over and that these are the same pre-processing steps that we're going to apply to incoming arriving data during the inference pipeline. Let's wrap up with some SageMaker best practices, SageMaker pipeline best practices. For the single batch transform call, we didn't pass incoming arriving data into the SageMaker endpoint. This is because SageMaker endpoint has a limit of 5 megabytes of data that it can input to pass out predictions. For DeepAR, this goes against DeepAR best practices, because DeepAR best practices dictate that we use the entire historical length of the target variable plus the prediction length of all the dynamic covariates, and this very quickly exceeds this limit. Instead, a best practice is to write this data to S3 and then instead pass the S3 file location into the batch transform call to perform the predictions and output this for our pipeline. For debugging inference pipelines, this can be extremely frustrating and extremely tricky to trace an error back through a pipeline. One thing that is helpful is that CloudWatch logs, they specify in exactly which container an error originated from. This means that a best practice would be to perform your transform on each individual step and verify that the output and the input are correct, that are being passed between containers. Richard and I hope that this content is going to prove useful for you. We plan on hanging around a little bit if you have any questions that you want to ask us. Thank you.